I think I should just keep. Yeah, I do too. Okay. So if that I'll plan for that. Okay. Okay. All right.
Did Lynn get her thank you?
Did she what?
Did she get her thank you?
Oh, her envelope? Yeah.
Yeah.
Okay.
Sure.
Yeah.
I don't know why that's down there. You think it's okay?
I don't know.
I think it's okay.
Okay. I'd like to get started, so if I could have everyone's attention, please. We're going to get started now, so if you could take your seats, please. Let's get started. Everything good to go?
I'm going to move this a little bit out of the way.
Okay.
I don't need to have it recorded.
Okay. Okay, can everyone hear me? Okay, let's get started. I'm going to be giving the second and third talks on statistics. I invite you, if you have any questions at any time, to please raise your hand, and I'd be happy to answer your questions. I'll try to pause and ask you if you have any questions. So it's going to be a two-part lecture, and I think I'll do what Lynn did in the first lecture, is have you stretch in between so that it doesn't seem to be too long. Okay, so again, my name is Karen Haglund. I'm from St. John Hospital and Medical Center, and the first part here is to talk about research designs and potential interpretation of data and introduction to statistics. I'm very happy to be here. I've worked with residents at St. John's for 26 years, and I've helped them through all phases of their research projects, so I'm well equipped to give you kind of the best advice as residents starting out. Most of you, I think, haven't started yet, so you're thinking about your research studies. So I hope I can be of value to you to help you through that. Okay, let's see if the first slide advances here. It seems like we had trouble with that with the first lecture. Okay, so far not working. I'm just doing a right-click, Dave, on the remote. Have to use the keyboard, you think? Okay, let me try the keyboard. No, that's not working either. Page down. Okay, let me have a pause here till we figure out how to advance. Click my mouse. I was told not to because then it's going to go off the slide and stop the recording. So I don't really want to do that. Okay, let me get some people here to help. Sorry about this. I didn't want to click the mouse because I thought that might harm something. Do you think so? Okay, so now it's going again? Yep. Okay. Yeah, it is. Okay. All right, I think we're up and running. Thank you. So I think it's easiest when you have kind of a daunting task ahead of you is to take it step by step. So I'd like to go through the steps, and I did this last time as well, if you were here at the first research workshop. And if you go online, you should see a handout that has all these steps outlined for you. But first you want to identify a topic, and this can really come from anywhere, your interest and effort that you've made with certain as you're making your rounds with your clinical topics, literature review. Variables of interest have to be defined. You have to come up with a testable research hypothesis, design your study, do what's called a power analysis to see how many subjects you need, write a research proposal or protocol, design data collection tools, go through your various committees, such as the IRB, if it needs review, collect your data, set up a spreadsheet to enter your data, and then actually enter your data. You can perform a statistical analysis, which I'm going to be talking about today. And hopefully you have somebody at your institution to help you with this. Does everybody have somebody at their institution? Raise your hand if you know somebody that would help you with this. Okay. Most of you are nodding or raising your hands, so some of you aren't, so that's worrisome. Hopefully you have somebody at your institution to help you with this. Graph your data to see what's going on. Create slides or a poster of your data for presentation, and write your paper or manuscript. So, are you confused by statistics? Well, I'm going to try to make it clear today on some of the basic statistics that you need. So your goals are to understand why a particular statistical test was used for your research hypothesis. So you meet with your statistician, he or she goes through the various tests, but you have to understand not necessarily how to conduct those tests, but why they were used, and to interpret your results, and to understand and evaluate the medical literature. So you also need to know something about statistics for your journal club. Not really to perform your own calculations. So there was a study, it was done a while ago, in 1983 in the New England Journal of Medicine, but they looked at all the literature that was published in that year, and they tried to figure out what level of expertise was necessary to understand the statistics. So you could actually understand 58% of the statistics if you just knew descriptive statistics, like means, standard deviations, medians, and so forth. If you understood what a t-test was, then you would grasp 67% of the literature. And then if you could understand contingency tables, epidemiological statistics, this is just really sensitivity, specificity, negative and positive predictive value, Pearson correlation, regression, analysis of variance, then you would understand 84%. So you have a good grasp of the literature if you just get up to that level. And I think that, this paper is old, so I think statistics have gotten a little bit more advanced over the years. But I still think it holds true that you don't need to be a statistical expert in order to understand the literature. And a lot of the tests you see are really variations on these basic themes. So before you choose a statistical test, you have to figure out the type of variable that you have. So what scale is it measured on? Is it qualitative or is it quantitative? And you have to figure out your goal. Are you comparing groups? So you're trying to see which group lowers their systolic blood pressure more than the other. Are you trying to measure a relationship or an association between variables? So those are different types of goals. And so there are 4 different scales of measurement: nominal, ordinal, interval, and ratio. And nominal and ordinal are lumped together as qualitative data, and interval and ratio are lumped together as quantitative data. And so let's start with the simplest scale, and all of you will be collecting data measured on a nominal scale. So it's the simplest scale. The variables have no numerical value. They have categories, and you count the percent in each category. So for example, if you collect gender, you have 2 categories, male or female. You have race categories, marital status, whether or not a tumor occurred, or alive or dead. So these are variables that just have categories. They don't actually have numbers that you can add and subtract, multiply, and divide. So when you enter the data, you may assign them numbers. You may say, okay, for males, I'll just put a 1 in the Excel spreadsheet, and females, maybe I'll put a 2. But you wouldn't take an average gender then of 1.5, or you wouldn't perform any kind of mathematical manipulation. You would just count how many 1s you have and how many 2s you have. Okay, sorry for that service announcement here. Okay, ordinal scale moves up a little bit in the measurement. And so here you don't just have categories, but you have an order to them. And so you can rank them from highest to lowest. The intervals may not be equal. And so if you think about, let's say, a race, everybody can relate to that. So somebody comes in first place, somebody comes in second place, somebody comes in third place. So maybe your first place winner comes in 20 minutes, and your second place winner comes in 20.5 or 20 and a half minutes. And then the third place winner comes in 24 minutes. So those are not equal intervals, but yet you can say first place, second place, third place, and order them. So examples in medicine, cancer stages, APGAR scores, pain ratings. You've seen pain ratings on a scale of no pain to the most excruciating pain. And so the patient will circle a 6 or a 7 maybe on a pain scale. And what I call Likert scales, and you've all seen that too when you're asked to circle a number from 1 to 5, 1 being strongly disagree, 5 being strongly agree. And so that would be a Likert scale. So those are ordinal scales where there's order to the categories. Interval scale is more quantitative data. And the only example that anybody ever gives for this is temperature on a Celsius scale, because you don't have a true 0 point. And so usually you're not going to have any data measured on an interval scale. But you will have data measured on a ratio scale, which is where you have a true 0 point. So here you can do all mathematical manipulations. So examples would be age in years, body weight, blood pressure, length of stay, time in the OR. So all of you will have variables measured on a ratio scale in your research projects. So why I bring this up is that it leads to different types of statistics. So if you have nominal and ordinal data, it would lead to non-parametric statistics. And if you have interval or ratio data, it leads to parametric statistics. So they're different types of statistics. Okay, so when you came in today, you should have gotten a little clicker to measure your audience response. Does everybody have a clicker? Okay, so we'll try this now. Hopefully this will work with all our technology going today. So the first question we have for you today is, which of the following does not characterize nominal scales? Is it A, a score in one category must be counted the same as a score in another category? B, you can count the number of categories and scores? C, you can add and subtract the scores? And D, it is the most appropriate scale for variables that vary in non-quantitative ways. So choose your answer now, please. Carly, I'm not seeing any answers coming in. You're clicking? Okay, good. It usually tells me up at the top there responses, and I'm not seeing anything. Maybe they're coming in. I don't know. Everybody click their answer? Let's see if it works. No, it did not. Okay. Well, that's okay. For some reason, they're not being picked up. we don't seem to have the technology God smiling upon us today. The correct answer here is that, remember, this does not characterize a nominal scale, so the correct answer was C, that you can add and subtract scores. You cannot do that because you don't. So we're just saying gender is 1, female is 2, so you wouldn't want to, take an average gender, for example. So something on a nominal scale, you just count up the number. Okay, so that second question is, and we can just call out the answer since our clickers aren't working. Identify the measurement scale here for the species of bacteria within a culture. So whether that be nominal, ordinal, interval, or ratio. So nominal, right. Okay, so we're just going to list the different types of species, and we may give them a number when we enter the data rather than typing out the name of the species. It's better just to make a list and say, you know, each species is a certain number. But that would be nominal data. So good. And then what about the observed stage of a pressure ulcer? What would that be? Ordinal. That's good. Okay, because it's a stage. So you're ranking those from less severe to more severe. So that would have some order to it, so it would be ordinal. Good. What about hospital length of stay? What scale of measurement would that be? Ratio, okay, because that's a real number. So it's a number of days. So you could say, you know, the average length of stay was 3.5 days, plus or minus a day. Good. Okay. So what I want to talk about now are two branches of statistics. So we have descriptive statistics and we have inferential statistics. So descriptive statistics are our first step in analyzing data. The goal here is not to come up with a p-value, but it's just to communicate your results. And an example would be, let's say I do a study on 105 people, and I ask them whether they're smoking or non-smoking, or I pull that information from their chart. And so at the bottom here, this is actually a clip of SPSS, which is the statistical software I use and a lot of people use. There's two main packages. There's SPSS and there's SAS. And so probably the person you work with will work with one or the other. So you can see here I've got on the left-hand column, I've got smokers and non-smokers. I've got 26 smokers and 79 non-smokers. And then I've got 22 people where I don't know what their smoking history is. Maybe it wasn't recorded in their chart. So then I would take the column that says valid percent, throw out my missing, so my denominator now would get rid of those 22 people. And so I would then say I have 24.8% that are smoking and 75.2% that are non-smoking. So you definitely want to do some descriptive statistics. It's usually reported as Table 1 in your paper. So it's just the basic demographics of your population, typically, or the characteristics of your population. So you definitely want to count up how many each category you have and then give the percent. And if I ask them how many cigarettes they're smoking, I see here that it ranges from 1 to 100 a day. And again, I've got, so that's for my 26 smokers. I'm missing are all the people that don't smoke. And then I can see kind of where my, kind of how the distribution is. And then from there, I can calculate some descriptive statistics on those 26 people. So the average number of cigarettes smoked is 19.62, plus or minus the standard deviation of 20.3. My minimum is 1, my max is 100, so my range is 99. So typically I would report the mean plus or minus the standard deviation. Sometimes you see the median listed instead, and usually that's for a skewed distribution or one that's not normally distributed. So an example would be if I were recording people's salaries, and let's say I took a bunch of people working at this hospital and asked them their salary, came up with an average. Let's say the last person I asked was Tim Cook, the CEO of Apple. And I threw his salary in, and I calculate an average. Well, the average now is going to be artificially inflated. Okay, so it's not a good way of representing the sample, but the median would be. The median is like a median in the highway that divides the highway, so you have half above and half below. So the median would still be representative of what we call the central tendency. Okay. So let's shout out our answers again. Which measure of central tendency is important to people who want to think they are in the better half of the population? Is it the mode, the median, the mean, or the standard deviation? Median, yeah, okay, because that divides it down the middle. So if you're in the better half, you're above the median. Which measure of central tendency is important to people who want to think they are, oh, got the same one again, sorry. Okay, so that's it for the clickers for now. Let me also talk about confidence intervals, because a lot of times you also want to report confidence intervals of your results. And journal editors are requiring this more and more, so you see this very commonly. So this provides a range in which we are reasonably likely to find the true value. So it gives a way of representing the data other than just whether the p was significant or not, but what the range of the true value is. So the p-value tells you, and what is the p-value that most people are looking for? Less than 0.05, right, so that's the line in the sand. So that tells you whether you have an effect or not, right? So you're all looking for the t to be less than 0.05. But if you calculate a confidence interval, you can actually talk about the effect size and how much impact that has. So for an example, which statement gives more information? So statement 1 is that the difference in 1-year survival rate between the experimental and control groups was significant. The t is less than 0.01. Okay, so that's good. So I know that we've got different survival rates, got a significant p-value. Yes, you have a question? Yes. So it doesn't have to be one or the other. It actually should be both. Yes. Yeah, I mean, in the past, people have just looked at p-values and said that was the mark in the sand, but it's better actually to report the p-value and the confidence interval. That gives you more information. So in the second statement here, we have the 1-year survival rate increased by 20% in the experimental group with a 95% confidence interval of 14 to 24%. Okay, so I could still put the p-value in that statement, but now I actually know what their survival rate is, that it increased by 20%. And I know that I'm 95% confident that the true range is between 14 to 24. So I think my best guess is that it's 20%, but it could be as low as 14. It could be as high as 24%. And I'm 95% confident that the true number is in that range. Okay, so that gives you a little bit more information, the second statement, than the first statement. So the 95% confidence interval means that in 95% of the replications, so if I were to repeat the study, the true value of the population would be within that interval. And you can use the confidence interval for means, for percentages, for relative risk ratios. And you calculate this, and it comes out in your SPSS output, but to calculate it, it's your effect size plus or minus a critical value times the standard error. And for the 95% confidence interval, the critical value is 1.96. And so you would take that and you would multiply it by the standard error. So you have a narrow confidence interval. Okay, you have less variability. It's generally associated with a larger sample size, and you get more information about the true effect. So you can hone in on it more carefully, closely, what the true effect is. If you have a wide confidence interval, it doesn't give you as much information. There's a lot of variability associated generally with a small sample size. So you really want to look for a narrow confidence interval. That's a better thing to have. If a finding is non-significant, that the t is greater than 0.05, and you have a narrow confidence interval, that implies that no real difference exists. Okay, so you're very confident in that. If you have a wide confidence interval, it really implies that you didn't have enough subjects and you have a lack of power in your study. So some examples here. Let's say smoking and bladder cancer. So what if I say that smokers had an increased risk of bladder cancer, and the relative risk ratio is 1.9 compared to non-smokers, and the 95% confidence interval is 1.3 to 2.8. Okay, so if the confidence interval includes the null value 1.0, then the p-value will also be non-significant. Okay, so in this case, it doesn't include that. So we know that this is a significant finding, that the relative risk is 1.9, increased risk of bladder cancer compared to non-smokers. Amoxicillin and a urinary tract infection. Is a single dose of amoxicillin more effective than 2 weeks of therapy for treatment of a UTI? Single dose is a 61% cure rate. After 2 weeks, we have a 74% cure rate, and the p-value is just missed significance at 0.07. This was actually something that was published. And the 95 confidence interval is a negative 1.5 to 27.5. So you can see why this was not statistically significant, because the confidence interval contains the null value of 1.0%. And so you know that the p-value must be non-significant. It's also a very wide confidence interval, so it's a lot of variability on what the effect size is, and so that gives you less confidence in the results as well. Okay, let's take a stretch break before I move on to the next part. Okay, let me start again. Before I start, are there any questions on what I've covered so far about descriptive statistics, about confidence intervals? Any questions at all that I could answer? Okay, so then let's get into statistical testing then, please. Okay, so in this section, I'm going to be talking about inferential statistics. And so I'm moving away from descriptive statistics. This is what you think of when you say you need somebody to help you with statistics. It's the inferential statistics. Am I good, Carly? I'm recording? Okay, very good. Okay, so everybody have your attention again. Come back to the part 2. All right. So we're talking about inferential statistics. So this is where the fun begins. This is the part of my job that I love the most. I actually love getting an Excel file and answering the research question. It's exciting because you've worked on your study, you've collected your data, you've entered the data, and now we actually need to get to the point where we can answer the question that you have, you know, is this treatment effective over a placebo, or whatever your research question is. So I actually love running the statistics to help you get to that answer. So inferential statistics, there's an inference here, and the inference is from the sample that you collect to a larger population. So you're not interested in just making a conclusion about, let's say, the 50 or 100 or 1,000 people that are in your study. You hope to generalize it to a larger population of people. And so that's what you're going to do with the inferential statistics. Non-parametric tests are used for nominal and ordinal variables, so that's why I spent some time on that. And it makes no assumptions about the data. So those are easier tests to run. Parametric tests, you have to have interval or ratio data, and it does make assumptions of data. And they're the same assumptions throughout all the tests. You'll hear the same phrases again and again. So the data should be normally distributed. You should have what's called homogeneity of variance. So in my example where I asked a bunch of people, middle-class people, what their salary was, and then the last person I asked was Tim Cook, I wouldn't have homogeneity of variance, right? I would have a problem there because I'd have a lot of variance because I included a billionaire in the sample. So you don't want to, so that's a problem if you have data like that. And you want to have independent observations, that each person's data is entered in once into the spreadsheet and is accounted for once. So which test do you use when you have data? So you need to know the scale of measurement, and you need to know your goal. Are you comparing groups? And how many groups do you have? Because that's going to make a difference. And then are you measuring a relationship or an association between variables? So these are the most commonly used statistics, and you probably had statistics in medical school. Raise your hand if you did. Yes, did you have some exposure? How many of you remember what you learned, though? Okay. And that, you know what it's called? It's called use it or lose it. So by the time you're a resident, you've kind of forgotten about that. So maybe you had to really know that very well for your MCAT. And then, you know, as a resident, you're not using that very much. And then all of a sudden you have to do a research project, and all of a sudden you have to remember your statistics again. So it's difficult. But these are the most common statistics. So chi-square is a very common test that I'll talk about today, and all of you, I'm pretty sure, will be using that in your studies. There's a subcategory of that called a Fisher's exact test. Then there's a t-test when you have two independent groups. And independent groups would be the unpaired t-test. If they're dependent, let's say a pre-post test, and that would be a paired t-test. But in any case, it's when you're comparing two groups. If you have three groups or more, then you would move to an analysis of variance or ANOVA. And then if you're looking at a correlation and you have ratio scale data, you would use a Pearson's correlation. If you want to look at regression, then you would do a linear regression. And so those are the tests for the most part that I'll cover today. And this will cover a lot of what you'll do as a resident on your studies. Okay. So let's say I have a study where I think there's some kind of relationship between smoking and socioeconomic status. So I have these two categorical variables, and I want to know if they're associated. I shouldn't really say correlated, and a lot of people will say correlated. Correlation is really variables that are ratio scale variables. So when they're categories, it really should be associated. So you have smokers, and they're either smoking or non-smoking. So I have 26 smokers and 79 non-smokers. And then I've divided my people into a low, middle, or high socioeconomic status group. So I would have had to have operationally defined those groups, maybe based on their income and so forth, or their insurance status. Okay. Let's see. I can get that off the screen here. Okay. So what this is, again, a little clipping from SPSS, statistical software. And how you read this is you have 6 cells.
Muted.
And the first number in each cell is the number of people. So you have 7 people that are smokers that are in the low socioeconomic status. And then you have the percent within socioeconomic status in each of those cells. And so you would interpret this as 38.9% of those in the low socioeconomic status group are smoking, 20.3% in the middle socioeconomic status are smokers, and 26.1% of the high socioeconomic status are smoking. So maybe I have some kind of hypothesis that those in the lower socioeconomic status are maybe less educated about the ill effects of smoking. Maybe they're more stressed due to their low economic status, that they're working a couple of jobs and they're smoking more. You know, I could have all kinds of theories here. So, you know, the question is that higher than the other two groups? And so I would actually run a statistical test to look at that, and it would be called a chi-square. And that would be the symbol for it. Very common test association between categorical variables. And I'm looking for the difference between what's called the observed proportion and the expected proportion. So what I actually see versus what I would just expect by chance. And I have to be careful of how many people are in each cell. If I have too few, it's not a good test to run. So in this case, I can actually run it, and I get this output. I take the first row, which is the Pearson chi-square value, and I've circled it, and it's 0.268. That's my p-value. Okay, that's always the p-value that we're trying to find. And so it's not less than 0.05, obviously. So I have to conclude then that there's no association between smoking and socioeconomic status. So I have my numbers up at the top there. I can still report my percentages. I mean, those don't change depending on the p-value. I still have those 38.9, 20.3, and 26.1. But I have to conclude that those are just chance fluctuations, that they could just as easily be jumbled around because my p-value is 0.268. I could be making what's called a type 2 error. There could actually be an association here, but I didn't have enough subjects to show it. I didn't have enough, maybe I didn't have enough smokers in my study, which is good for them, but not good for my study. So, any questions on that? So that's a very common statistical test to use, the chi-square. Now, I said that there's a problem if you don't have enough subjects in each of those cells, if you have a number of cells that are less than 5 subjects in each. So there is a way around this, and it's called a Fisher's exact test. It's named after a statistician, Fisher, and it's based on what are called exact probabilities. So you use this when the expected count is less than 5 cases in each cell, and it comes into play when you have a 2-by-2 contingency table. So I couldn't have used it in the last example because I had what's called a 3-by-2, because remember I had 3 categories of socioeconomic status, and I had 2 categories of smoking. So 3-by-2 is a 6-cell design, so this would have to be a 4-cell design to use this. But I could use it, let's say, in this example. Let's say I'm interested in the relationship between smoking and lung cancer, which seems absurd to us in 2017 that we would not know that relationship. But remember, back in the days, as I told you about last time I was here, the 1940s and 1950s, the journals like JAMA, New England Journal of Medicine, were very happy to run ads saying that, 2 out of 5 physicians preferred Camel cigarettes to any other brand. And those were ads, full-page, glossy, colored ads in the medical journals advertising cigarettes. So we didn't always know the relationship between smoking and cancer. So let's say I take my 105 people in the study, and again, I got my 26 smokers and my 79 non-smokers, but now I'm going to look in their charts and see if there's any history of lung cancer. And I find 4 unfortunate souls that have a positive lung cancer. 3 are smokers and 1 is a non-smoker. And so that's 11.5% of my smokers have lung cancer and 1.3% of my non-smokers have lung cancer. So I run my test on this, and I'm going to use the Fisher's exact test, and it comes up automatically in SPSS when you have a 2-by-2 design like this. And my p-value is 0.046. So I've reached statistical significance, haven't I? That was enough to show it, that there is a relationship between smoking and cancer in my 105 people. Okay? And does that make sense? Okay, so you've got another test there that's similar to chi-square, but it's used in the specific case where you have a 2-by-2, or we have fewer, people in each cell. So when I only had, 4 people with lung cancer, 3 smokers and 1 non-smoker, this is a good way. Another good test to use then is the Fisher's exact, because I can get around those low ends that way. Okay. So any questions on chi-square? Everybody good with that? Okay, so I can guarantee you will be using chi-square in your studies. So let me move on now. I'm going to be talking about t-tests next. And so now my hypothesis has something to do with BMI and smoking. So people always say, well, if I quit smoking, I'll gain weight. So maybe there is some kind of relationship here. And so I'm going to take my 26 smokers and my 79 non-smokers, and I'm going to look at their average BMI. And so the mean for the smokers is 25.2, if I round up, and non-smokers is 26.2. Got my standard deviation there. So is that a difference? It looks kind of small to me, but we'll test it statistically and see if that's different. And so here I'm going to use what's called the unpaired t-test or student's t-test. And it was actually put forth by William Gossett. And William Gossett, he kind of has an interesting backstory I'll tell you about quickly. He was a quality control supervisor at a Guinness factory in Dublin, Ireland. So those of you who are beer lovers, maybe you'll be able to appreciate the story. And he was actually publishing some trade secrets about the beer industry. And so he was going by the name Student so that he could hide his true identity. And so that's why it's called the Student's T-Test. But it was actually William Gossett. And it's a very common test. When you have two independent groups, and you want to see if there's a difference between them. So remember I told you at the very beginning, I said you got to figure out what kind of statistics you want. Are you looking for a difference between groups, or are you looking for a correlation or an association? So here you're looking for a difference between groups. And you want to make sure that what you're measuring, the outcome, or what's called a dependent variable, is a true number, a continuous number measured on a ratio scale. And you've got all those same assumptions of a parametric test that we talked about. And so here's the data here. So again, those were the DMIs, plus or minus the standard deviation, the mean plus or minus the standard deviation at the top there. And then I've clipped in the actual output from SPSS. And my p-value is 0.4. So is this something to get excited about? No. So I've got to conclude that BMI is, there's no difference in BMI between the smokers and the non-smokers. So I kind of thought that with the eyeball test. But when I ran the t-test, it confirmed that. So not different. You know, there could be an effect here. Maybe I didn't have enough subjects. But it looks like if there's any effect, it's going to be a real small one. So not a lot of support for the hypothesis. So I would say that I failed to reject the null hypothesis here. Okay, let's move on to a paired t-test now. So let's say, like a lot of physicians, I'm very concerned about my patients who are smoking, and I want to do something to help them. So let's say I put them in some kind of a program, some kind of intervention. Maybe they're learning more about the ill effects of smoking, watching some videos, getting some instruction, and so forth. So I count the number of cigarettes on average that they're smoking before the intervention. It's just under a pack a day at 19.6. And then I run my intervention, and lo and behold, it drops to 11.3. And so I say, wow, that's good. It went from about a pack a day to about a half a pack a day. So did my intervention make a difference? From the eyeball test, it looks like maybe it did. So we're going to run what's called a paired t-test. So the previous one was unpaired, but now it's paired because these are the same observations on the same people. Okay, I'm counting cigarettes smoked, and I'm doing it before the intervention and after the intervention. So I line them up in my Excel spreadsheet. I've got a column for what they smoked before and what they smoked after, and I'm going to look at the difference between the two. So the observations are dependent here. It's what's called a within subjects design, like a pre-test, post-test, pairs of observations. So I set up the pairs, and I look at the difference in the score. Did a change occur that the mean difference is not 0, or there's no effect that the mean difference is about 0, or not significantly different from 0. So that's how it works with the paired t-test. And again, I assume that that I have a normally distributed set of data, both the before and after cigarette consumption. And so again, those were my descriptive statistics at the top, that I had about 19.6 cigarettes plus or minus 20, so it's quite a bit of variability. And then afterwards, not as much variability, and the mean comes down to 11.3. So I run a paired t-test, and I get all these numbers at the bottom here. Tells me my mean difference is 8.3 cigarettes that they dropped. And way to the right then is the statistical significance. That's the p-value, and that is 0.016. So that's good, right? Less than 0.05. So that means that I actually made a difference in my study. I helped these people, and they not only probably have a clinical advantage of smoking less to their health, but they also have a statistically significant drop. So I've got clinical significance and statistical significance, so that's great. So my intervention did help. What about if I have 3 groups of people? So let's say I take my smokers, well, actually all my people, and I put them into 3 categories. So I have 79 non-smokers, and then I take those same 26 smokers, and I'm going to call them light smokers and heavy smokers based on their cigarette consumption. And I'm going to define light smoker. Remember, you have to always operationally define. You can't just say a light smoker and a heavy smoker. You have to say what that means. So a light smoker, I'm going to say, is less than a pack a day, and a heavy smoker is at least a pack a day. And I'm going to go back to my hypothesis that maybe there's a difference in these folks in their BMIs. And so I'm going to calculate their BMI. So I have the mean column there. So the non-smoker's BMI is 26.2. Light smoker is 26, round up again, 26.2. And heavy smoker, I only have 9 of those people. Good for, good that I don't have so many, but not as good for me statistically. But I have 23.3 is the mean for those folks' BMIs. Standard deviations are all kind of similar, so there's good homogeneity of variance here. I've got my 95% confidence interval, so look at that. I can tell you the lower bound and the upper bound, so that's good. And so I've got all those statistics printed out in SPSS, but the question is are the BMIs different? That the ones that are heavy smokers look like they were a little bit lighter, but we have to ask if that's statistically significant. So I'm going to use a test, not the t-test this time, but I'm going to use an analysis of variance, or what's called an F-test, for Fisher again. Fisher comes into play here again. And you hear ANOVA, it's the acronym, is analysis of variance. So 3 or more independent groups. And I want to test for a difference between the groups. And the outcome is ratio, like before, the same assumption. So you've heard these things again and again on these slides. So for the parametric test, you see these same assumptions. And so again, those are my descriptive statistics at the top. So I'm really looking whether the heavy smoker's BMI is significantly lower. And so I run my analysis of variance. I get my F statistic. I get my significance value. I've circled it there, and it's 0.310. So it's non-significant. And so I must conclude then that there is no difference between the BMIs for my 3 types of folks: smokers, non-smokers, light smokers, and heavy smokers. So those numbers could just as easily be scrambled around. They're all just the chance fluctuations. Okay, so that's all that is mean. When you hear the fancy term ANOVA, analysis of variance, it sounds very complicated, but it really isn't. I'm trying to make it real simple for you because that's the easiest way. And so, this is all it means. You're just looking at 3 different groups of people, and you're trying to see if there's a difference in some kind of real number. It could be length of stay, it could be systolic blood pressure, it could be BMI. So, in that case, my p-value was not significant. But what if it were? What would I do then? I would have to do what's called post-hoc t-test. And it would be multiple comparisons of every possible combination. And there are a lot of different types of post-hoc t-tests. In SPSS, you'll get a dialog box, and you click on which one you want. And so there's the LSD, or least significant difference test. There's the Duncan test, the Newman-Cool's, the Tukey's honestly significant difference test. So it kind of makes me chuckle. These honestly significantly different. Bonferroni and Chaffee. So these are all statisticians' last names, and they reach their Hall of Fame here with their different tests. And they vary in terms of how conservative or lenient they are, in terms of the likelihood of making a type 1 error. So type 1 error is when you throw out the null hypothesis and you say, yay, I got an effect. Rah, 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 I've got an effect. And perhaps you shouldn't have said that. You jumped the gun and don't really have an effect. So the Chaffee test is the most conservative. That's the one I usually pick for the post-hoc t-test, because if it'll pass the Chaffee test, it'll pass the other ones. Duncan test is the most liberal, so you're more likely to make a mistake and say, hey, I've got an effect when I don't. Newman-Cool's is kind of in the middle. That's a general rule of thumb. So there's a lot of these different tests. So let's say that I have a study where I look at heavy smokers, and I look at the number of cigarettes they smoke per day after 3 treatments. And so I have some people in treatment A, treatment B, and treatment C, and I'm recording the number of cigarettes they smoked. And so here's the mean plus or minus the standard error in this case. So it looks like if I were a physician, I might favor treatment B, and that it got me the people, people that were, it was the group that smoked the least amount, treatment B. And so I think that maybe that's the group to root for here. So when I run my analysis of variance on these three groups, I see that they are statistically different from each other. The P was less than 0.001. So I say, well, that's good. But then the question is, well, what does that mean? I mean, it looks like treatment B is different from treatment A and treatment C, but maybe not. I mean, I need to take these three groups and make a listing of every possible pair combination and see if those pairs are different. And so that's why it's called post-hoc t-test. It's like a t-test in that you have two groups of people, but it's post-hoc, it's after the analysis of variance. So you only do this if your analysis of variance was, your p-value was less than 0.05, that you reach significance. So overall, then it tells us there's a difference between the groups. It doesn't tell us which ones are different from one another. So this can get very complicated if you have a lot of groups. You get long tables of all these pairs, and you have to go through it and pick out the ones that are significant. So in this case, remember my B group is the lowest. So when I run the pairs, A versus B are different. Okay, so that's good. And B versus C are different. Good. But A and C are not different, which I didn't think they would be because it's 27.4 versus 27.6. So I get a p-value for each possible pair combination. And so I know exactly where my effect lies. Any questions on that? Okay. Let me move on to then the variations of analysis of variance. So you'll hear these different terms in the medical literature, and it may seem kind of confusing, but they're all analyses of variance. But a one-way analysis of variance is you have one independent variable and one dependent variable. So remember that from last lecture that the independent variable is what you're manipulating as an experimenter. So that's your treatment. And the dependent variable is what you're measuring as an outcome. That's what you're interested in studying. That's your outcome. A two-way ANOVA is what's also called a factorial design, and that you have two independent variables and one dependent variable. So you're still measuring one thing, but now you're looking at two independent variables. So now what's interesting in here is that you can test for an interaction between the two, as well as what's called the main effect of each variable. So it kind of mimics the real world. So we know if we're trying to get somebody to decrease smoking, there's probably several different things that are going on into that. So maybe it's the intervention we're doing, but maybe it's something else as well, okay, that's related to that we're measuring. So we can look at a couple different independent variables. A repeated measures ANOVA is when you have a within subjects design and your observations are dependent. So you're looking at the people over time. So maybe you're looking at their systolic blood pressure 1 month after treatment, and 2 months after treatment, and 3 months after treatment. And multiple analysis of variance, which is called MANOVA, it's the same as an ANOVA, except there are multiple outcomes or dependent variables. Okay, so we get more complicated that way, and then we're looking for a variety of dependent variables. Still, though, when you hear these terms, I think you should remember what the basic ANOVA is and not be too confused by these other variations of it. Okay. So now what I'm going to do is I want to look at if there's a relationship between these variables. And so I'm going to move into a correlation analysis. So I want to see now if the number of cigarettes smoked is at all correlated with BMI. And so I've got two columns in my spreadsheet. I've got the number of cigarettes smoked, and I've also recorded the BMI. So to look at this correlation, I'm going to run what's called a Pearson's correlation. And again, it's named after a real live person, Carl Pearson. And so he lives on in this name that I'm sure you've heard. It measures the degree of relationship between two variables. The assumptions, again, are that the variables are normally distributed, that the relationship is linear, so as one variable increases, the other one decreases or increases. That's a linear. If you have a curvilinear relationship, then this isn't going to work. So that's why it's important to graph your variables and see what kind of relationship it is. That your outcome has to be measured on a ratio scale, and that it's measured on the same subjects. So when I have those two columns, the BMI and the number of cigarettes smoked, I have those two data points for each person. So it's the same subjects. I have the BMI and I have the number of cigarettes. And so when I graph the data, when I run the correlation, I can get, these are three different types of scatter plots that I might get. I'm actually not going to probably get the perfect correlations, but anyway, my R value can range from -1.0 to +1.0. So you want to be at one or the other ends of this continuum. Sometimes residents think, well, if I have a negative correlation, that's not as good as a positive correlation because it has the word negative in it, but that's not true. You want to either be at -1.0 as close as possible or positive 1.0. So on the left-hand side, then, if you have a perfect positive correlation, as X increases, Y increases, and all those points would fall on a line, and you would have a perfectly straight line. If you had a perfect negative correlation, it would be an inverse relationship. As X increases, Y decreases. And if there's no correlation, you can't draw any line at all. You just have a bunch of scatter. So you really want to be at one end or the other. A lot of times in studies, though, you'll get a correlation, let's say, of 0.2 or 0.3. Those are small effects. If you get 0.5, 0.6, then you have a larger effect. Very hard to get close to a positive 1.0 or a negative 1.0. So there are rules of thumb as to how big the effect size is and kind of how to categorize it. So in the example I gave you, those two columns of data with BMI and number of cigarettes smoked, I run the correlation, and the correlation I get on that is a -1.69. So boy, that doesn't sound very good, or does it? Because I want to be close to -1.0, and so it's only -0.169. Sounds pretty close to 0 to me. And there's also a p-value associated with that, which is 0.410, which of course is non-significant. So if I draw that out, which you should do, you can see that I can draw a line indicating an inverse relationship, but it's not very good. Look how much scatter there is across the line. So if I look at the number of cigarettes smoked and the BMI, I can, I've got the person that's smoking 100 cigarettes. The BMI is kind of on the lower side of things. So, and I've got all that scatter. It's really not on that solid line at all. So not a real good correlation between the two. I have to say there's no effect at all, no relationship. Okay, so that's the correlation. And so that's really only the time you should use the term correlated. Again, otherwise it's associated. What if I have a more complicated model and I want to predict the outcome? And a lot of times we want to do this in medicine. We want to predict who's going to live, who's going to die, who's going to succeed in quitting smoking, who's not. And so my outcome is the patients either quit smoking or they're still smoking at the end of my intervention. And I collect a lot of data on these patients. I collect the number of cigarettes they're smoking, their BMI, their social economic status, their gender, maybe some other things, but that's what I've got on the slide here. And so what I want to do now is do a regression analysis. I want to generate an equation to predict the outcome variable based on one or more input variables. In other words, predict Y from X. Got the same assumptions again. I've got the linear association, normal distribution, and we're measuring on the same subjects. So a simple linear regression is one outcome, one independent variable, and they're both continuous. A multiple regression analysis is as a single continuous outcome, but I'm going to throw several independent variables in the model. And a logistic regression, which is used a lot in medicine, so you should pay attention to this because you are very likely to use this, is that you want to predict a binary outcome. So in medicine, we want to know who's going to have a disease, who's not going to have a disease, who's going to be dead, who's going to be alive. So I've got a binary or dichotomous outcome. And I've got several independent variables. Are we trying to go to sleep here? That sounds like a nice nursery rhyme. I hope my stats lecture isn't that boring. All right, so logistic regression is, you never know what's going to happen when you give a lecture. You've got to be prepared for anything. So logistic regression is when you have a dichotomous outcome. So it's used a lot in medicine. And you've got a number of variables you're going to throw in the model. Okay, so again, I'm looking at who quit smoking. I have all those different things I'm going to throw in. So it's kind of like a witch's brew. You're throwing everything in the pot and seeing what bubbles up to the top. And so if I don't know anything in my study, I just predict that everyone is going to smoke, which is the classification table at the top. I would be right 61.5% of the time that the people are still smoking. But if I throw in all those variables that I showed you, that actually goes up to 76.9. And so that shows you then that knowing those other variables increases my predictability. And so I do what's called a stepwise linear regression. I put in each variable as a step. And the number of cigarettes smoked before my intervention was significant at 0.024. That's the step that was entered in first. And then the other variables are not in the equation, the BMI, the socioeconomic status, and the gender, because none of those were significant. And so this is what's called a logistic regression model. I'm putting in all these variables and kind of seeing which one is significant. It's more complicated than looking at each individual variable one at a time. It's what's called a multivariate analysis. And so more and more you see pressure from journal editors to say, you know, let's do a multivariate analysis. Let's just not look at univariate analyses, but look at a multivariate analysis. Because now you're pitting the variables against each other and really seeing what matters. And so the only thing that matters here for predicting whether somebody quit smoking or not in my study is how many cigarettes they were smoking before. It doesn't matter what their BMI is, what their socioeconomic status is, or what their gender is. So you can see the power of this in that you're looking at, that's why it's called a multivariate, multiple variables at the same time. So it's a good step to do. Okay, any questions on that? Okay, so let me move on now to non-parametric tests. So what happens if you don't meet the assumptions of a parametric test? Okay, so you've got a problem with homogeneity of variance, maybe your data are not normally distributed, maybe you have a small n. Well, you can use a non-parametric test. And I'm going to show you here on the left-hand side are the parametric tests, and on the right-hand side are their equivalents in the non-parametric tests. So if you have a problem using an unpaired t-test, because you don't meet the assumptions, you can use what's called a Mann-Whitney U-test. So if you see that phrase in the literature or that's used in your study, again, it's two groups, you know, if you don't meet all the assumptions, you can use the Mann-Whitney U. So it's equivalent to a t-test, but it's a little bit easier on the assumption. So it's the Mann-Whitney U test. For a paired t-test, you can use the Wilcoxon Sine-Ranks test. For ANOVA, you can use what's called a Kruskal-Wallis test. And for Pearson's correlation, you can use Spearman's row or Spearman's rank correlation. So there are equivalents in the non-parametric world to the more commonly used parametric tests. But the parametric tests are pretty robust, so most of the time they are used. But if there's a good reason not to use it, then you can use the non-parametric equivalent. So I just put this up here so that if you see these terms, you kind of are familiar with it and you know what it means. Yeah? If you can, I think your question, I couldn't have had a hard time hearing you, but if the data are normally distributed, if there's a test for that? Oh, okay. Yeah. I would say that if you have less than 30 people in your study, I would use a non-parametric test. I would use a non-parametric test if your data are not normally distributed, and there are a test for that too. You know, what will happen is when you run your And I didn't point this out in the output, but it was there if you look back at your slides. For the t-test, analysis of variance, there was another test that was run. For the t-test, it was called the Levine's test. And so if that's significant, then there's a correction on the t-test output for when the assumption of normality is not met, and then you use the corrected p-value. Okay, so if you work with your statistician, they should know that and be able to give you the right numbers there. So that was a good question. Any other questions? Okay. All right, so let's test your knowledge here. So we're going to play a little game called Name the Statistical Test. So I'm hoping that you picked up on what I was trying to put out there. So the question is, do residents improve their knowledge after a lecture as measured by the number of correct answers on a quiz before and after the lecture? So would I use analysis of variance, chi-square, a paired t-test, or Pearson's correlation? So the thing is here is it's going to be, I'm going to look at whether they improve their knowledge, number of correct answers before and after the lecture. So that whoever said paired t-test is correct. Okay, because I've got a pre-post test design. So that is correct, the paired t-test. What about this? Patients are randomly assigned to one of three groups, low dose, high dose, and placebo, and the effects on systolic blood pressure are compared. So would I use analysis of variance, Fisher's exact test, Student's t-test, or logistic regression? ANOVA, yeah. And the big clue to that is that it's three groups. If it were two groups, we would have used the Student's t-test. Is there an association between smoking status and socioeconomic status? So would I use a Mann-Whitney's U-test, the Pearson correlation, a Tukey's test, or a chi-square? So smoking status and socioeconomic status. So it sounds like categorical to me, because I'm saying status. So smoking status, I'm thinking non-smoker, smoking, socioeconomic status, maybe I'm thinking low, middle, high. So what would I use? Chi-square, yeah. If I actually counted number of cigarettes and dollars made per year, then I would have used correlation. Okay, is there a relationship between length of stay and number of medications prescribed when a patient is discharged? Is that logistic regression, Pearson's correlation, repeated measures ANOVA, or chi-square? Length of stay, the real number, number of medications, real number. Want to look at the relationship between the two, so what would I use? Pearson's, yes, Pearson's correlation. Okay, so I'm going to see if those two are correlated. Okay, so I think you did pretty well, or at least the ones that caught up for an answer did well. All right, so in wrapping this up, interpretation of results. The size of the p-value does not indicate the importance of the results. So I want to stress that. Even though I love statistics and I'm really looking for that p is less than 0.05, sometimes I can get that on a trivial effect. You know, maybe somebody is smoking 1 cigarette less per day. That's not really that clinically relevant, and it reached statistical significance. So you got to look at it from a p-value point of view, and you've got to look at it from kind of common sense and whether it makes a good clinical difference. And you have to interpret your statistics right. So I tried to stress that today, that you're looking at differences between groups, or you're looking at an association or a relationship. So you want to make sure when you discuss your results, you use the right language. You want to say one group is lower than the other. One dropped more in systolic blood pressure than the other. Or you want to say that socioeconomic status is related to smoking status, is associated. Or you want to say that, you know, if it's a correlation, then that's a correlation or a relationship. And of course, remember that correlation does not imply causation. So a lot of journalists, when they report research studies in the media, kind of make this jump that just because something is correlated, that they kind of infer cause and effect, and you really can't. So you don't want to overreach the conclusions that you're entitled to make. So remember the difference between clinical and statistical significance. Also remember to allow plenty of time. So I emphasized this last time, but allow plenty of time to conduct your study and particularly your statistics. You know, I've had residents come to me on a Friday and they have to get their presentation Monday morning, and I get their data on a Friday afternoon. And so I'm miserable, they're miserable, they don't understand their data by the time they present it, and it really shows. So if you allow enough time, you can understand your results, you can grasp them really, you know, really understand them so that when you present, you're really an expert. And it also allows time for sub-analyses. So you could look at different groups of people. You can say, I've got an overall effect, but maybe it's different between males and females, or maybe it's different between the races. So I can do subgroup analyses, so I have more time for that. You want to find somebody in your institution that can help you with the statistics. I certainly hope you don't have to do them on your own. There's certainly software you can download for free off the internet and run your own chi-square and t-test, but it's kind of garbage in, garbage out. So if you're not really knowing what you're doing and putting it in correctly, you're going to get something that looks like you've got a p-value, but you may have not done it appropriately. So really seek somebody out to help you with this. And then know why you conducted each test. So you probably won't know the mechanics of running the tests and so forth, but once those tests were done, you should know why they were done. So if somebody questions you and said, why did you do a t-test? You can say, well, because my outcome was continuous and I had two groups of people, so that was appropriate to run a t-test. And so you can defend your statistics when you present them. So you've got to understand why you use each test. So remember, there are three kinds of lies, damned lies, and statistics. This was popularized in a autobiography by Mark Twain, so don't lie with statistics. All right. Any questions? Okay, very good. Thank you. Let's take a 10-minute break.
It was helpful, and you talked about the confidence intervals. I haven't come across this before, so you gave me that the progression-free survival is for 20 months, but it says that it's not estimate.
Oh, wow, that is strange.
And this is like a good study, and it's about letrozole and other drugs.
I don't understand that.
So that doesn't
really...
That's
the lower end at 22.1.
So is that still okay because it's like way out of the line of no difference? But you do need to know how narrow.
Yeah, I don't, you know,
that's weird.
I really don't understand it. Yeah.
So I recognize an oncologist. Yeah. Because he knows the actual study. Okay. But I thought that was kind of weird.
It is very weird. I have to tell you.
I haven't come across that.
No.
And then we talked about hazard ratio. And just if I'm interpreting it correctly. Like, for example, so they have patients with non-visceral disease and give percentages of the two groups. Hazard ratio is 0.5, so it's just like a relative risk,
It's
right?
very similar to a relative risk, yeah. So they're less at risk because it's below 1.
If they're in the treatment.
Yeah.
Less at risk for dying. Okay. Okay, thank you so much.
Oh, you're very welcome. I don't know if that's... We're just having so many tech problems. Yeah. Right. Yeah. I think so. Yeah. Yeah. Right. Yeah. Yeah. A lot of glitches. Yeah. Yeah. Something. Yeah. I don't know. It was. Oh, that's okay. You know, I'm used to those things happening. Yeah, we just shouted them out, so it worked fine. Yeah. Yeah. And then one point, too, during my talk, it came up on the screen that the audio was not, yeah. So I don't know what they were seeing or hearing over in Lansing. I think we're we're trying to do too many things, maybe. Yeah. Yeah, I don't know. We'll have to rethink it.